Hello, and welcome to this video on electromagnetic waves, types of EM wave and their properties part 1, and this is for GCSE Physics and Combined Physics, and don't forget to like and subscribe. All electromagnetic waves are transverse waves. They transfer energy from source to an absorber. They form a continuous spectrum, and all electromagnetic waves travel at the same speed in a vacuum, which is 3 times 10 to the 8 meters per second. And they obey the wave speed equation, v equals f lambda. The difference between the waves is the change in frequency and wavelength. Learn the order of the waves: radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays, and how the wavelength, frequency and energy changes as you go along the spectrum. To recap some definitions, frequency is the number of waves passing a point each second, and the wavelength is the distance from a point on the wave to the equivalent point on the adjacent wave. As you can see in the diagram, as the frequency increases, the wavelength decreases, and this can be shown using the wave speed equation. Wave speed equals the frequency multiplied by the wavelength, or v equals f lambda. All electromagnetic waves travel at the same speed in a vacuum, 3 times 10 to the 8 meters per second. So if the frequency increases, to keep the speed at the same value, the wavelength must decrease. These two values, wavelength and frequency, are indirectly proportional to one another. One of the properties of electromagnetic waves is that they transfer energy. Some examples are as follows. Infrared radiation. When these frequencies of electromagnetic wave are incident on materials, the energy is absorbed and the temperature of the material increases. Conversely, when a hot object gives out heat, it is giving out infrared radiation. Microwaves. These frequencies of electromagnetic wave are absorbed by water molecules. The water molecules gain energy and start to vibrate. The energy is then given out as heat that cooks the surrounding food. Ultraviolet. UV light can give energy to electrons in some atoms. If the energy is the right amount, then the electron will move to a higher energy level. It will be in an excited state. When the electron de-excites, it will give out electromagnetic waves, and if these are in the visible light range of frequencies, we will see the object glow. When EM waves interact with boundaries between materials, they can be reflected, absorbed, or transmitted. What happens in each case depends on the material and the wavelength of the wave. For example, when light moves from air into glass, the following can happen. When the light hits the boundary, some of the wave's energy can be reflected. Some of the wave's energy is transmitted through the material and refracted on entry. And some of the wave's energy is absorbed by the material, increasing the temperature of the material. Another example is how radio waves and microwaves move through our atmosphere. To get from the transmitter to the receiver, some radio waves can curve around the Earth. Others, however, will be blocked by the curvature of the Earth. But these shortwave radio waves can be reflected at the ionosphere boundary. Microwaves, however, are not reflected by the ionosphere. They can travel straight through it, which means that microwaves are very useful for communication with satellites. This is how to construct a ray diagram of refraction of light as it passes from one material into another, in this case from air into glass. The normal is a construction line that is at 90 degrees to the boundary. The incident ray is a beam of light that hits the boundary at the same point as the normal meets the boundary. The angle of incidence is the angle between the incident ray and the normal. It can be measured using a protractor. The refracted ray is the ray after the boundary. The angle of refraction is the angle between the refracted ray and the normal. It can be measured using a protractor. In this example, the ray has changed direction and bent towards the normal. The angle of refraction is smaller than the angle of incidence. As the ray passes out of the block into the air, it undergoes a second refraction. This time, the refracted ray bends away from the normal. The angle of refraction is greater than the angle of incidence. When drawing ray diagrams, always use a ruler, and don't forget a protractor for your exams. We have seen that as the light moves from air into the glass, it bends towards the normal. This is because the glass is optically more dense than the air. This causes the light to slow down, and as it does so, causes the change in direction. As the light then moves out of the glass and back into the air, which is optically less dense than the glass, the light speeds up and bends away from the normal. If the light was incident on a boundary at 90 degrees to it, the light would still change speed, but there will be no angle to change. The light would continue through the block. Waves can also be drawn using wavefronts. Imagine looking at the waves in the ocean from above. You would see the crests of the waves moving towards the shore. These are the wavefronts. If we represent waves using lines, it is a simplified way of showing what is happening during refraction. This diagram shows the refraction of wavefronts when they are incident on a boundary. When the wave passes the boundary into the glass, it slows down. The part of the wavefront that goes through the boundary first slows down earlier, and in this model, this causes the wave to change direction. When the wave passes back into air, the part of the wavefront that goes through the boundary first speeds up first, and this causes the wave to bend away from the normal. As the wave slows down and changes direction, it also changes its wavelength. To understand what's happening, we need to look at the wave speed equation, v equals f lambda. When the wave goes into the glass block, it slows down, and v, its speed, is smaller, but its frequency, f, remains the same. For these things to be true, the wavelength, lambda, has to get smaller, which is why the wavefronts are closer together on the diagram. When the wave moves out of the glass and into the air, it speeds up. Frequency remains the same, so the wavelength has to increase. And that's all for this video. Thank you so much for listening.